Hello everyone, today we are going to see about n and n dash are the norm linear space. The set B of n comma n dash of all continuous linear transformation of n into n dash is a norm linear space with respect to the pointwise linear operation, and the norm is defined by norm of t equal to supremum of norm t of x such that norm x less than or equal to 1. Further, n dash is the banach space, then b of n comma n dash is also a banach space. We have to prove this. So first we take b of n comma n dash is the linear space. For that linear, we need to prove that linearity and boundedness. So we know that the set of linear transformation from one linear space to the another linear space constitute a linear space itself with respect to the usual definition of addition and scalar multiplications. So t1 t2 of x equal to t1x plus t2 of x, and t alpha t of x equal to alpha t of x. So it will be therefore sufficient to prove that set of all continuous, that is bounded linear transformation, is a subspace of the linear transformation or all linear transformations. Criteria for subspaces: we have to take alpha beta belongs to that W subspace, and A B belongs to F field. Alpha A alpha plus B beta belongs to subspace. So first what we take means consider the two transformation t1 and t2, that is belongs to b of n comma n dash. Then by the definition of boundedness we have norm of t1 of x is less than or equal to k1 of x, norm of t2 of x is less than or equal to k2 of x. So for each for some k1 and k2 there are greater than or equal to 0. So norm of alpha t1 plus beta t2 of x equal to norm of alpha t1 of x into x plus beta t2 of x. So it is alpha into t1 of x plus beta into t2 of x. So less than or equal to norm alpha t1 of x plus norm beta t2 of x. So norm alpha modulus of alpha norm t1 of x modulus of beta norm t2 of x. So alpha into t1 of x can be written as k1 into norm x, and modulus of beta can be written as k2 into norm of x. So if we take the norm common means we get mod of alpha k1 plus beta k2 norm x. So k is norm of x. So norm of alpha t1 plus beta t2 of x less than or equal to k into norm x. So alpha t plus beta t2 is bounded. Bounded implies that continuous. Hence it is belong to the B of n comma n dash, and therefore it is the subspace. Hence it is a linear space. Subspace, and hence it is a linear space. We have to show that B of n comma n dash is a normed linear subspace. For that we need to show the four conditions that should satisfy the norm conditions. So t belongs to B of n comma n dash. By the definition we know that norm t equal to supremum of norm t of x and norm x less than or equal to n. We have to prove the axioms of the norm on the elements of B of n comma n dash. So since norm t of x is greater than or equal to 0, by definition itself we know that norm x clearly norm t by definition of t. So norm t is by definition of t, supremum of norm tx is greater than 0. By definition we know that norm t is greater than 0. Then we have to prove that norm t equal to supremum of norm t of x, norm x less than or equal to 1, x belongs to n. So if we divide this side means norm t of x divided by norm x, x not equal to 0, x belongs to n. So then norm t, this value, if norm t equal to 0 means then this whole term also equal to 0 implies. So 1 by norm x norm t of x equal to 0. So it will become as norm x is less than or equal to 1. So 1 by norm x is less than 1. So norm tx, x belongs to n, x does not belongs to 0. Okay, x belongs to n, so x does not belongs to 0. Then norm t of x equal to 0, norm t of x equal to 0, x does not 0. belongs to 0, x belongs to n. So norm, so tx equal to 0, t equal to 0. It is a 0 transformation. Otherwise, it is known as 0 transformation. Then alpha t of x is alpha into t of x, norm of alpha into norm t of x. That is alpha t. Alpha t can be written as supremum of norm of alpha t of x such that norm x less than 1. So supremum of mod alpha norm t of x. So that is less than 1. So alpha into supremum, that is norm of alpha t of x can be written as norm alpha norm t. Sorry, mod alpha norm t. T1, T2 can be taken as supremum of and put x inside, and then split the norm, then later substitute the supremum. So norm t1 norm t2, so norm of t1 plus t2 is less than or equal to norm t1 norm t2. So b of n comma n dash is the norm linear space. First we have to prove that it is a linear space, then it is a norm linear space. Then what we do means we have to prove that b of n comma n dash is the banach space whenever n dash is the banach space. So we have to prove that n comma n dash is the complete whenever n is complete. So Tn be the Cauchy sequence in b of n comma n dash. Norm of Tm minus Tn less than epsilon for all m comma n greater than or equal to 0. For any fixed x in m, we take that norm of Tm of x minus Tn of x such that norm of Tm minus Tn of x less than or equal to norm T of Tm minus Tn norm x. So Tn is the Cauchy sequence in x belongs to n. So Tn is the Cauchy sequence Cauchy sequence in n dash, and for each x belongs to n. So n dash is complete, hence the sequence is convergent. We know that the n dash is complete, hence the sequence is convergent. For that there exists a unique y. Okay, n dash is complete, for that there exists a convergent sequence in n dash. So we take the Cauchy sequence in n dash, then there exists a unique convergence, there exists a unique y equal to t of x in n dash, that limit of tn of x equal to y for a fixed x in n. So this defines the mapping as t of n to n dash, t of x equal to y, limit of tn of x. We will show that t is linear. We have to show that t is linear bounded. Okay, for linear x1 x2 belongs to n and a be the scalar, then t of a x1 plus a x2 equal to, we take that limit of tn of a x1 a x2, substitute the limit a t of x1 plus t of x2 by linearity, a into limit of t1 of x1 plus limit of tn of x2, and then a into this can be written as t of x1 plus t of x2. Then boundedness, we t of x, limit of tn of x, limit of tn of x, norm. If we take the limit outside means norm t norm x, so less than or equal to norm t of tn of x. So it is supremum of for tn alone, so norm x. So tn is the Cauchy sequence, but tn is a Cauchy sequence. We know that norm tm minus tn less than epsilon. So modulus of norm tm minus norm tn less than or equal to norm of tm minus tn is less than epsilon. So tn is the Cauchy sequence on the real line and hence convergent and bounded. So there exists a k greater than 0, such that tn is a Cauchy sequence on the real line and hence it is a convergent sequence and bounded. So there exists k greater than 0, such that supremum of norm t of x is norm tn is less than k, less than or equal to k for k greater than 0. So by condition norm t of x is less than or equal to supremum of norm t of x norm x. Supremum value is less than or equal to k norm x. So t is bounded. Finally we prove that t is bounded. So t is both linear and bounded. So it is belongs to linear and bounded means it belongs to the b of n comma n dash. Now we have to prove that tn converges to t. Tn converges to c. T. So Tn is the Cauchy sequence. We know that the form norm of Tm minus Tn less than epsilon, m comma n greater than or equal to 0, x belongs to n, norm of x is such that norm of x less than 1. We have given that Tnx converges to Tx, hence by the definition there exists a positive integer nx greater than or equal to n naught such that norm tx minus tnx, norm tx minus tnx less than epsilon n greater than n naught, norm of x less than 1. So norm of tnx minus t of x is equal to norm of tn minus tnx of x plus tnx of x. So split the norm and we get this term alone. So we know that norm x is less than 1. So this is norm of tn minus tn of x plus norm of tn of x minus t of x. This is epsilon, this is another epsilon, 2 epsilon. So norm of tn of x minus t of x is less than 2 epsilon for n greater than n naught, norm x equal to 1. So supremum of tn of x minus t of x, x belongs to n, norm x less than or equal to 1. Instead of that we can replace that tn minus t of x less than t of x, x belongs to n, norm of x less than or equal to 1 is less than 2 epsilon. So n greater than or equal to n naught. Then what we do means norm of tn minus t less than 2 epsilon. So t is less than epsilon, n greater than or equal to n naught for defined by definition of norm t, by definition of norm t. So tn converges to t when epsilon tends to 0. So b of n comma n dash is the complete and therefore it is a banach space. Hope you all understand and thank you.